So we're going to talk now about rotational energy. That's going to be the easy part of our day-to-day, and then we're going to get to the harder part of our day-to-day, which is moment of inertia. But we'll see why moment of inertia comes up as we talk about rotational energy. All right, so for rotational energy, somebody took all of my props. That's really disturbing. Okay, if something is spinning in a circle, hey guys, go and find a seat. We're actually doing things now, so I need people to have a seat. This is on videotape, so come on. All right, if an object is spinning in a circle, its center of mass might not be moving. And so your initial thought might be, okay, well then it doesn't have any kinetic energy because the circle, this object, whatever it is itself, its center of mass is not moving. So its velocity, translationally, is 0. So if you wrote out its kinetic energy, you might write out 1/2 m0 squared and get 0 kinetic energy. The problem with that idea is that aside from the exact location of center of mass, every other particle that's a part of this object is moving. So we moved from the particle idea where we only consider center of mass, and we only think of it without any size or shape. The center of mass by itself is not moving, so our original kinetic energy does not exist. But since now we use the rigid body model, and this object is made of a size and a shape, and all the other particles that make up it, all the other particles that have mass are moving, this must have some energy. So, rotational energy is the energy of a rotating object. I know, shocking. Because all the particles and the object are actually spinning. So they are actually moving. So it has to have some sort of kinetic energy. Now, to calculate this, it's not going to be super shocking. K rotational is just going to be the sum of every particle's kinetic energy. So however many particles make up this object, I'm going to add all of them together. Obviously, the particle at the very, very center isn't moving, so that guy gets left out, but all the other particles have some amount of mass. They're moving at some sort of velocity. Now, that's a little bit of a tricky thing. Because this object has size and mass, all of those particles spread out through the radius of this object are going to have a different velocity. So it would be really taxing to say, I'm going to write out the individual mass and velocity for each of these. So it might be helpful if I replace V. What is V equal to? Omega R. So what if I say it's R squared and W squared? That makes it a little bit nicer. Now I just need to know the mass and where everything's located. So where is the mass? Because 1/2 is a constant. For every single particle, omega is going to be constant because they're all stuck on the same object spinning at the same rate. They're all going to do the same amount of revolutions in the same amount of time. If you're ever like, are we sure about that? Are we 100% sure that if I'm on a rigid body and we're spinning, everybody's going to do the same rotation? Yes, I know this because I am an object on a sphere that's rotating, and I experience one rotation every 24 hours, just like you, just like people on other continents. This is true. So if I pull that out, I get this, 1/2 W squared times this sum of the mass times the radius squared. This is an idea of where on my object is the mass. There are a variety of objects in all sorts of shapes and sizes, so my mass can be distributed in an infinite number of ways. But that's what this term does. It says, how is that mass located? So we gave this a term. We said this is actually a thing. And we're going to call that thing the moment of inertia. So, moment of inertia gets a fancy variable too. Moment of inertia is I is equal to MR squared. If it's just one object that's like out on a thing. Let me give you an example. Like I have this box on a massless rod, so it kind of looks like a hammer. And I'm spinning it from this point right here. That's an example of when I can use just this straight, simple equation. This is a massless rod, so it doesn't count. And this mass, let's say it's 5 kilograms, is located a radius away. So the moment of inertia for this is explaining that all of the mass is located this radius away. So its moment of inertia would be the mass times whatever that radius is. Now that's great for a single scenario like this, but what if instead I have 2 blocks? Right? Now my moment of inertia might be I is equal to m1 r1 squared plus m2 r2 squared. But I come back to an issue here, which is, what is the radius? What is the radius that I put in this equation? And here's a really key thing about moment of inertia. Moment of inertia is dependent on the pivot point or the axle location. I have to determine where this object is spinning to figure out what the moment of inertia is. This r is the distance from the pivot to the mass. So, my moment of inertia for this theoretical barbell thing that I've created here. It's so funny that still when you draw a barbell, people use like balls, like a barbell with the balls on the end. That's how they draw it. And I've never seen that once in my real actual life. But let's say that this is, I've stacked some weights. They're really small because this is only a 5 kilogram total thing. It's massless in the middle, so I'm just lifting 10 kilograms, 20 pounds. But let's say that that's my dumbbell here. It wouldn't matter where I put the pivot point. If I spin it around the center, then I would have a mass of 5 kilograms. Let's say this whole thing is 1 meter. I would have a mass of 5 kilograms, 0.5 squared away, and a mass of 5 kilograms, 0.5 squared away. What if, instead, I put the pivot right here? I'm holding one edge of it, and it's spinning around that way. Now, this mass, what's its radius? 0. So it's going to fade out, and the only thing I see is this mass here. So my moment of inertia just dropped because of that. Does that make sense? So moment of inertia is dependent on the location of the pivot. If I don't know where I'm pivoting from, I can't figure this out. So especially if you're in a scenario where they say something's pivoting around its center of mass, and it's not like an equal location, you might have to go find the center of mass. Then you can find the R. Actually, no, one of the practice problems does this next week. You have to find the center of mass first, then go back and say, okay, how far is everything from that center of mass? Question?
How would you treat you're spinning it around the first 5 kilogram weight, how would you treat it as having 0 radius if we just said that it doesn't?
If I'm holding one of the 5 kilogram weights, right? So it's rotating around that, somehow it's spinning through that 5 kilogram weight, then that weight is now located at the axle, and so it's not spread out. When we think about moment of inertia, we're thinking about how much mass is away from that axle or pivot point. Since that 5 kilogram mass is we're treating like a single particle, its center of mass is at the axle or pivot point, then it doesn't count at all. Right. If I'm doing this with multiple objects like this, and we'll do a couple examples like that, and then we'll do a couple with like solid objects, then I treat those as particles. Yeah, absolutely. The rigid body is the combination of the massless rod and those 2 pieces. But those pieces I treat as located at their center of mass. Good question. All right, let's do an example. So we're going to do an example here. I have a widget. If the widget has 100 millijoules of kinetic energy, how fast is it spinning? So what is W? You're like, what's a widget? Well, there's no, I mean, this doesn't really have a name, okay? That, and then this guy, and then, oh, that's not a square, gosh. And then this guy, and then there's a rod connecting here. And the axle is gonna be right there. This is 8 centimeters away, this is 10 centimeters away. This one is 300 grams, this one is 250 grams, this is 100 grams. So the first thing I'm going to do to solve this question, I have an equation for it right there. K rotational is 1/2 W squared times this moment of inertia. So I could write that as K rotational is 1/2 IW squared. I have K rotational, it's 100 millijoules, and I'm looking for W, but I need an I. Yeah.
Wait, is that like always what a widget is?
No, it's just like, oh, they're using the term widget for something.
Oh.
Instead of object, I don't know. That's just what the example said, so I'm calling it a widget too. I mean, when I think of widget, I think of the little squares on the phone, so, right? That's what those are too. Those don't have a moment of inertia, fun fact. They do not. They are massless, so. All right, if I find I have multiple masses, so I'm going to add them all up. So I'm going to start with the 300 gram. That would be 0.3. It's located 0.08 squared away. Plus, should I include the 250 gram? No, I should not, because it's located at the pivot point. So then the only other one is 0.1 squared. If I do that math, I get 0.00292. What are the units for moment of inertia? What are the units for this? If I'm multiplying mass times r squared. Kilogram meters squared. It's a weird one, but that is true. All right. So to solve my question, I've got K rotational is 0.1 of a joule. Is equal to 1/2 this 0.00292 times W squared. So W in this case, I didn't remember the number from previously. 0.1 divided by 0.1 divided by 0.5. And then I take a square root? No. 0.1 divided by 0.5 divided by 0.00292. All the buttons. 7.89 rads per second. Questions on this? It's the same way I would do a kinetic energy question. If it said this object has a amount of kinetic energy, a mass of this, what's its speed? It's the same kind of question. Okay? Let's do one more example. But before that, what happens if I have an object? So not necessarily a collection of masses that are all together with something. I have some objects. So I'm going to give you some of the basic ones. The question I get as I write these out is, do I have to memorize them? And let me break the bad news. In APC, unlike AP1, you do, in theory, have to memorize these. The reason for that is because I'm about to give you a tool after this next example to find these guys. So with that tool to find them, they don't have to give you them because I'm going to show you by finding the thin rod through an end and a disc/cylinder. So, sadly, you do either have to memorize them or do the calculus to find them. Now, if you're like, I'm never going to do the calculus, I would much rather just memorize. I feel you. However, they are going to give you at some point a weird moment of inertia for some weird shape that they've come up with all on their own. And you're going to have to figure it out. So knowing how to do the calculus is not necessarily a negotiable thing. Can you get out of it by knowing these? Absolutely. But will you have to be able to understand the process of how to get these? Probably, yeah. So, knowing this, these are specific objects. So I have a thin rod through the center. I have a thin rod through the end, a disc or a cylinder. Discs and cylinders are the same thing. The only thing that varies is their width, right? A disc is 2-dimensional. A cylinder is 3-dimensional. Hoop, that's going to be also called, what do you think another word for a hoop is? A spring? A spherical shell, that's the one. This hoop would technically be just a shell, and then a spherical shell would be the other one to go with solid sphere. But hoop just means all the stuff is on the outside. So, second example. A 1 meter long, 200-gram rod is hinged at the end. And connected to a wall. What is its speed when it hits the wall? So, what I'm saying is here's the wall. This long piece is here. It's going to rotate at a pivot point located right here, and it's going to go through an arc and hit the wall. So eventually it will be here and swing down, right? That's the idea there. Okay, so we're going to do this with energy because energy is the thing that we have already in rotational. We have also talked about kinematics, but we're going to do this one with energy. So, what kind of energy did this rod start with when it was just magically chilling in the air? Versus now it's down here. If I think about its center of mass location is right here, and then it's down about here when it's done. So what has it lost? Gravitational potential energy, right? Gravitational potential energy. And what amount? What is this height? The full L? I would say 1/2 L. So mg 1/2 L is going to equal 1/2 I W squared. So mg 1/2 L. We have this I, so this is a great moment on a test if you don't have to go find it. If you have to go find it, you're going to be sad. But I know what it is. It's 1/3 ml. So 1/3 ml squared, W squared. Hey, the mass cancels out, so that's nice. An L cancels out, so that's nice. A half cancels out, so that's nice. So I get G is equal to 1/3 L W squared. So W would be equal to the square root of 3G over L. How do I get, it did not ask for angular velocity. It asked for speed. So how do I turn W into V? Times radius, right? Times the radius. So what would the radius in this case be? L. So L, square root of 3GL, it works out to be the square root of 3G. That L. Woo! And if you do the math for that, it gets you to 5.4 meters per second. So it's just the same energy. I turned potential into kinetic. The thing about this is that, yes, my center of mass is moving, but I was also going through rotationally. So, questions about this example? That's going to sum up rotational energy. We're going to spend the rest of class really talking about this moment of inertia. I'm going to leave these guys up. But what do we do if we need to go find a moment of inertia? Well, the good news is we have an equation for this. If I extrapolate on this summing of masses, if I keep summing all the masses, right, over infinitely small masses, and therefore infinitely small lengths, I would get an equation like this. I is equal to the integral of r squared dm. This is going to feel a little bit like the center of mass linear density stuff. That's why, again, we went over it in the last class. It's going to feel a little bit like that. I'll tell you this, the integral is in no way the hard part, okay? We're going to go through several examples of these throughout classes, okay? Because I'll tell you what the hard part is. I'll point it out. If you can do it in your head, if it makes perfect sense to you, I've said this in this class before, let me say it again. Stop wasting my expo markers by drawing random stuff. And also, go do a mathematics degree. Go do a mathematics degree if this makes perfect sense. All right.
I have a question.
Yeah.
Where does the M come from?
The mass?
Yeah.
It comes from the original kinetic energy equation, mv squared, and then I turned m r w.
Like in the integral.
And the what?
In the integrals.
It comes from the same place. It's saying that I'm summing radius squared times these tiny changes in mass.
Oh, that's changing.
Yeah. All right, so let's do it. We're going to do a thin rod about the end, rotating about the end. That's what we're going to do first. So I have this integral, just like for linear density and center of mass, this is integrated to dm. I don't want to integrate to that because the variable that I have in here is r, which is a distance, which means I need to take an integral in relation to distance. So just like we did before, we are going to find a way to rewrite this integral without dm. Okay? Now, the way I'm going to do that is the tricky part. This is the hard part. Writing out this statement is the piece that they're asking you to do. The actual integration is going to be a power function. It's not that tricky. Now, in this case, I have my mass, and it's over an entire length. Because remember, I'm saying that r is measured from the pivot point. R is measured from the pivot. So since I have the pivot at one end, this is over an entire length. So when I think about density, I'm thinking about mass over the full length is equal to dm dl. So I can solve for this if we want to do this. Let's say it's a thin rod on the x-axis. So that would be dm is equal to m over l dx. Choosing what this should be and what this should be is the hard part. So I'm going to start today by showing you what they should be, and then we're going to talk about the theory behind it more in the next couple classes, okay? Because at first you're just going to be, if I tried to explain it right now, you'd be like, what? This is a long thing. It's a one-dimensional thing, so I know that I should be integrating over a length. If I had a two-dimensional thing, what should I integrate with? Length. What if it's a three-dimensional object? We measure that in what? Volume. So I should do dV. If it's a two-dimensional object, I should use area. Okay, so that's a little bit of the basics there. So since this is a one-dimensional object, I'm using length. If I plug this in, the rest of this goes really smoothly. The integral from where to where? What are my limits? 0 to L, the length of this rod. And then it's ML times R squared, we'll say X squared dx. M and L, those are just constants. So I'm just doing X squared dx. What's the integral of that? 1/3 x cubed. And then I can plug in my limits and I get 1/3 L cubed. If I cancel out the L, I get 1/3 ML squared. Hey, look, that's exactly what it's supposed to be. So again, when I do this integral, I'm going to do one more for a circular object. When I do this, the hardest part is figuring out how to write this. Once you understand that process, which we're going to work towards, right now we're just seeing it done We're going to work towards that understanding. Once you can write this, then plugging it in and doing an integral should just be a power function. All right, I'm going to erase this and do one more. This one I'm going to do is a disk. So I'm going to do a disk. I'll draw a picture of the disk to help. This one's a disk. I'm going to start with the exact same integral, r squared dm. That's a weird m, but there we go. Okay. So if this is my circle with a radius big R, inside of it, it's made up of all these teensy, teensy, tiny circles. I can't even draw it as thin as I want it to. This is a change in little r right there. So I want to write out that same kind of density statement. The mass of this is spread over an area, because this is a two-dimensional object. The mass of this is spread over an area. So I'm going to do dm over dA. That gets me dm is equal to m over a dA. I don't know why I made that one look. Hold on, I'm in the middle of something. All right, so I actually cannot integrate with area. That would be an area integration, and we don't learn that in high school unless I don't know what the BC stuff is. So I'm going to change this from area back to length. So how can I replace this A with something in terms of a length?
Length squared.
Pi r squared is area, right? Pi r squared is area. Hold on one second. That's going to be big R because that's the area of the entire thing. Then dA, I still can't integrate with area. So I want to rewrite this in terms of a little dr. So if this is really, really tiny, that change in width, dr, is multiplied by, this is a really, really thin, almost just single circle with no width. What is the size of a single circle with no width? That would be a circumference, right? So 2 pi, this time little r.
And why is that?
Close the door for a sec.
Why is that sound little?
What? Because this was talking about the whole area of the whole circle. So it uses big R because big R is the radius of the entire circle. Now for dA, I'm talking about this little change in area for this little tiny interior circle. And it has a dr that's the little r because it's small. And it's a smaller radius than the whole thing, right? So it's a little r. I don't know how much of the radius it is, but it's not the full big R radius. So if I plug that in, I is equal to the integral from 0 to r of m over, I'm going to cancel out the pi.
But why do you have dr this time?
Hold on. Because it's a circle, so I don't know which way it's going, so it can't be dx or dy because it could be going any which way.
Oh, okay.
So 2m over r squared times r times, that's the whole thing from this. Now I need the r squared that was already in there, dr. So this piece here came from this statement I wrote over here. So the difference on this side is that I had a two-dimensional object, so I had to, instead of doing the density-based mass over length, there was also a width to it. So I had to do mass over area. I can't integrate over an area, so I had to break that into length in some way. For the total area, that's just the total area of my whole circle, my disk. For the change in area, that is the change in area of this tiny interior circle, which is basically just a circumference because I'm saying it's itsy bitsy width, right? Infinitely small width. So it's that times the width. Now, all of this stuff here is a constant, so it gets pulled out, 2m r squared. And then this is 0 to r of r cubed dr. I'm back to a power function. Hurrah! The integral of r cubed is just 1/4 r to the 4th. If I go ahead and put the limits in, that's 1/4 big R to the 4th. So cancel out, some canceling out here, I'm left with 1/2 mr squared, which is the moment of inertia for a disk. Okay? We're going to keep doing these and talking about them because I absolutely believe when it comes to the mechanics section and the rotational section, this moment of inertia is where they really do try and stump you on an FRQ. They give you some weird shape or some weird change of the scenario for the shape so that you have to actually think about this and be able to do this part. So we're going to keep working on that. Last thing before I finish up is the really nice thing. So far we have talked about that we can easily find the moment of inertia if we know where the pivot is. But if the pivot's in a weird spot, that can make our lives hard because all of these objects, we only have this pivot, we only have this integral for if it's in the center. Right? All of these have been rotating at their center or about one end or some known axis. What if they give me a circle and they're like, hey, here's the center of mass. This could be the pivot, but no, we've made this the axle. This is the axle over here. This is where we need the parallel axle theory, which simply says this. The moment of inertia around this axle is equal to the moment of inertia from the center of mass. So that main moment of inertia that we've already gone through, plus md squared, where m is the mass and d is the distance the axle is from the center of mass. So that's the parallel axle theorem. It saves your butt on a lot of occasions because it means you can just use the normal, disc, hoop, sphere, rod. You can use the normal moment of inertia that you already know. And if they just say, oh, but this circle is actually going to have an axle through this weird place over here. You're like, it's okay. I'm going to use that normal one plus just the mass times d squared. In my handwritten notes, I have a proof of how this works out. If you would like to see it, I'm going to spare you.